Okay, so we were talking about reflection and refraction, and we were looking at the interface between two dielectric materials that are isotropic homogeneous, non-dispersive, and linear. And we found that in looking at that interface, that the incident and reflected angles are the same, and the transmitted angle is related by Snell's law. So we have n1 sine theta 1 is n2 sine theta 2, and we have theta incident is equal to theta reflected. Or equivalently, we could say that the x component of the incident is equal to the x component of the reflected is equal to the x component of the transmitted wave vector. So this is ki, kr, kt, and so we answered the questions of what directions do the waves go, and then to answer the questions of how much field and how much power are reflected and transmitted, we had to break things up into TE. And in the TE case, we have that the electric field is out of the plane of the board. And so the magnetic field is like that. So this is theta 1 and theta 1. And then we have the reflected field out of the plane and the magnetic field in the plane. And then KT, we have the transmitted field out of the plane, the transmitted magnetic field in the plane. And we found that the reflection coefficient, we'll subscript with S for TE, we found that that's equal to N1 cosine theta 1 minus N2 cosine theta 2 over the sum of the two elements. So I'm going to do my normal shorthand for notation. And TS is equal to 2N1 cosine theta 1 over the same denominator as RS. So that's TE. And TM, we have that the magnetic field, the incident magnetic field, is out of the plane of the board, and the incident electric field is in the plane of the board like that. And then over here for the reflected, we have that the incident, or rather the reflected magnetic field is out of the board. The reflected electric field is in the plane of the board. And then over here at angle theta 2, we have the transmitted magnetic field out of the plane of the board and the transmitted electric field in the plane of the board. And we found that the TM reflection coefficient is N2 cosine theta 1 minus N1 cosine theta 2 over the sum of those two pieces. And then TP we have is 2N1 cosine theta 1 over the same denominator as part B.
Listen,
Yeah.
for direction of ER, I still have problem because I put my finger like this, so this is K.
For
and
which
this
one?
is-
TE?
No, TM.
TM?
Yeah.
Right?
So then E should be up.
Yeah, and this is because K hat cross, or K cross, no, K hat.
Cross H.
across H, R, or any H, is equal to minus, what is it, mu naught omega E. So it's that minus sign that's doing it. Yeah, good point. I'm glad you brought it up. Okay. And where does this come from? Yeah, it's just the Ampere's law. When you plug in for a plane wave and work it through, the curl turns out to be this thing. And the time derivative, we end up with that. Okay, so we have the Fresnel equations here for TE and TM that relates the amount of field. So R is reflected field over instant field. T is transmitted field over instant field. And you notice I didn't write a vector sign on top of ER or EY, or EI rather. So what do I mean by those symbols?
Just the amplitudes.
Just the amplitude. Okay. All right, and then we looked at reflectance, which is the reflected power over the instant power, and we saw that that's just magnitude squared of the reflection coefficient. And transmittance, which is the transmitted power over the instant power, is equal to n2 cosine theta 2 over n1 cosine theta 1 times magnitude squared of the transmission coefficient. And always we have that the reflectance plus the transmittance is equal to 1. Because these are lossless media that we're talking about. Okay, so that's where we got to. Any questions? Yeah.
If you want to find the absolute value S squared for R, then we need to write it R like RS plus RT or what?
Well, so this is sort of generic, and really, the reflection coefficient is either the TE or the TM reflection coefficient. So if we have some arbitrary polarization state instant, we have to decompose it into its TE component and TM component, treat them totally separately,
And then some.
and then add them up.
Okay.
Yes, exactly. Okay, so now what we want to do is dive in and understand what these things mean and develop a good intuitive understanding as well as working understanding. So, to do that, we're going to first of all consider normal incidence, meaning that theta 1 is 0 degrees, and therefore theta 2 is also 0 degrees. So let's say that we're looking at RS, then cosine of 0 is 1, cosine of 0 is 1, so this just becomes n1 minus n2 over n1 plus n2. And then the reflectance, of course, is just n1 minus n2 over n1 plus n2 quantity squared. And similarly, we could write down TS and this transmittance, but I'm not going to bother. You can do that. What I want to do is focus on an example. Let's say we have an interface between air and glass in the visible. And so air has a refractive index 1.0, glass, let's say, is 1.5. And so we have light incident on that interface, and what we want to know is how much is reflected. And let's just look at it in terms of the reflectance. So the reflectance is going to be 1 minus 1.5, so minus 0.5, over 1 plus 1.5, so that's 2.5 quantity squared, and that's 0.04. So in other words, at normal instance on an air glass interface, we expect 4% of the power to be reflected. So if we don't have an anti-reflection coating, just a good rule of thumb, 4% of the power at each interface will be lost. Yeah?
Just a quick question, when, like, an anti-reflection coating, does that just like create like a intermediate index to like help it transition?
We're gonna go over that in detail later in this class. We'll see exactly how it works. We'll do single layer anti-reflection coatings, 2-layer anti-reflection coatings, and once you have those down, then anything else is reflected. But yeah, we'll see exactly how it works. As directly analogous to impedance matching on a transmission line with a quarter wave length of the transmission line of the right, in that case, characteristic impedance. In our case, it'll have to be the right proprietary impedance. Okay, so a couple of things. Let's say you're in your apartment and it's nighttime and you have a window in your front room. I assume you have a window in your front room. And you've got the lights on. And you look out your window, and it's dark outside. What do you see? Yourself. Yeah, you see yourself, right? It's like your window is a mirror.
It's reflecting everything. It's really just 4% of what you're seeing.
Yeah, so let's see how that works. So here's your window, and this is the inside. So here's you, and here you have some ambient light, whatever the room lights are. So let's say the irradiance is I room. So you've got some light incident here, I room, and you have basically 4% of I room coming back at you. So you got light incident on you, it scatters. The scattered light that goes to the window, 4% of it reflects back. Whatever goes into your eyeball, that's what you're seeing. Okay, and in the meantime, you have the dark night out here, and it's instant on that window. And so, how much of it actually makes it in?
96%.
Through a single interface, and then the glass actually has 2 interfaces, so it's 96% squared. But let's forget that. Let's just say 96%. So this is 96% eye dark. So the question is, what's the relative amount of light here versus here?
It's an SNR thing.
Yeah. Yeah. So let's say I room is 1,000 times bigger than I dark. Then this is going to be a heck of a lot bigger than that. By what? Factor of 40? So you just don't even see that. It's completely swamped by that. So that's why your window looks like a mirror. So how does a one-way mirror work?
Keep the other side dark.
Yeah, that's right. Just sit in a dark room. You know, if this is the police station, this is the interrogation room. Turn the lights off over here. Have a piece of glass, except rather than just going with the 4% reflection, put a little bit of partially transparent metal on there. So maybe you have 25% reflectance or 50% reflectance or something, which basically just boosts this and decreases that, but this is dark anyways, so now you've got a one-way mirror. It's very simple. Okay, how about You're in your car. It's dark. You've got your lights on. You can see, and you have that rear view mirror. And your rear view mirror has two settings, right?
Yeah.
Daytime and dark.
Yeah.
Okay. It's the same thing. So what happens?
Oh, it's 20 years old. I thought that was a diffraction. It's like this little like.
So here's you driving your car, and here is your rear view mirror. And your rear view mirror, this has a film of aluminum on it, and the glass is actually a wedge. And so what you do is you adjust this in the daytime so that light coming in, and I should angle this down a little bit, reflects into your eyes, and now you've got a nice rearview mirror. But at night, everything's dark, and you've got a car behind you with its lights on, and so you've got all this light coming in, and it just really gets in your face and is very annoying. So what do? You switch your rearview mirror to be on the nighttime setting, and all that does is it takes this guy and it tilts it. Oh, I think I got that. Yeah, I went the wrong direction. This angles down like that. What it does is it tilts it like this. So now this is the silvered part. So the light from the car gets reflected up onto the ceiling of your vehicle, the interior ceiling, and now you get a 4% reflection from that interface, and that's what goes in your eye. So you just blocked 96% of the light from the car's headlights behind you. And now it's not in your face, and it's not annoying and bothering you. And so a rear view mirror, all it is just a wedged piece of glass with the backside mirrored, and you're just flipping the angle when you go between day and night.
Okay, so when you flip it up, how do you get 4% down?
Pardon?
How do you get 4% down?
So I've drawn the angle a little bit off here. Let's draw it a little more carefully. So, so here's your head and your eyeballs, and what you want is for light to reflect into the aperture of your eye. And so what that means then is you want the glass to be at the right angle so that it reflects into your eyeball. And then what that means is that the mirrored surface here, the light that goes through, well, I didn't draw it at big enough angle. There we go. So this is mirrored. The light that goes through gets reflected up. Which is why, if you've got small kids in the back and they're fooling around with a flashlight or something, or they turn on a light in the back, suddenly when you look in your rearview mirror, you see the ceiling of the interior of your vehicle. It's because of that mirrored surface. That's why you want it dark inside the vehicle, so it doesn't screw up your rearview mirror. Yeah.
So when it's light, though, is the aluminum also putting some of that light back into your eye too? Is that the idea? So you tilt it the other way, and that way, like.
So this is the night orientation. The daylight orientation is you want this to go into your eye. So this is the back surface, and then the front surface does that. So the back surface, that goes in your eyeball. The front surface just, comes
the
down.
back surface is much more.
Yes. Mm-hmm. Yeah, and the front surface, it doesn't go in your eye, so you don't see it. But, if there's if there's, you know, something up here that becomes very bright, it's possible you could see something. But the ambient light from the outside is so much brighter that doesn't really happen. Okay, so now you understand one-way mirrors and rear-view mirrors. And it's just on the basis of this simple thing here. That's all there is to it. Okay, but I slipped something by you. At normal instance, is there a plane of instance? What is the plane of instance?
It's the interplane, but it's the interface plane.
No. It's the plane
Oh.
that the instant, reflected, and transmitted wave vectors form. They're always coplanar. So is there a plane of instance at normal instance?
I guess it could be any plane.
Yes.
Yeah, could be anything. They're all these planes contain all three wave vectors. So can I say that I have TE light?
Sure. Maybe.
Will it be any different than TM?
No.
No, it can't be, because, you know, there's no plane of instance. But if I, oh, and I should subscript this with an S. If I calculate RS, then that's minus 0.5 over 2.5, which is minus 0.2. If I calculate RP for the TM polarization, I get 0.5 over 2.5 because it's going to be N2 minus N1 over N2 plus N1. So this is positive 0.2. So what's going on here? It shouldn't matter which one I choose, but RS is minus 0.2 and RP is plus 0.2. They're different. What does that mean? Why are they different?
Well, what is the minus sign, actually?
Yeah, what does it mean? So if we go back to this, if we have a minus sign here, what does it mean?
Did you just switch the polarity? Okay.
In essence, yes. Let's go back to our drawing here. This is for TE. EI is out of the board, ER is out of the board. As we take these two wave vectors and bring the instance angle to 0, then notice the electric field is in the same direction. And this is saying I've got minus 0.2 of the instant field that gets reflected. So basically what the minus sign says is we guessed wrong. The electric field is actually into the board. So do we need to go back and redo everything?
No, it just put plus instead of
Just
minus.
flip the sign.
Well, I mean, the minus sign tells us what's going on.
Yeah.
So everything's consistent because the minus sign says what's physically going on. Okay, but notice here, as I take these and go to normal instance, what's my assumption about the relative direction of EI and ER?
It's opposite.
They're opposite. Therefore, I have a positive sign there. Because my assumption is already that they're opposite. So here my assumption is they're the same. Here my assumption is they're opposite.
So then the positive sign on RP is telling you that your assumption that they're opposite was correct.
Exactly. That's all. So is there any contradiction here?
No.
Not at all. Perfectly self-consistent. It all gets back to our assumptions about relative directions of the fields for the TE case versus the TM case. So, would it be conceptually nicer if we didn't have this? Maybe. But I have to tell you, I've only seen one book in several decades that makes a different assumption so that those signs turn out the same. Everything else, these are always the assumed directions. You always have that sign difference, the normal instance, because of the different assumptions of directions here for the electric fields. And it's perfectly okay. Not a big deal. Because the math will be consistent with our assumptions. But I just want you to recognize this, that, oh, even though these are different, really, because the assumptions are the same. Physically, they represent the same thing. So you'll never be caught by this, right? You'll never be confused by it. Okay. All right, so good, we've got that. Now, let's look at a different example. Again, normal instance. Let's say we have air, so refractive index 1, and diamond. And diamond, the refractive index in the visible is 2.4. So diamond has one of the highest known refractive indices in the visible. And so if we look at normal instance and look at what the reflectance is, then what we end up with is, 1 minus 2.4, so that's 1.4. 1 plus 2.4, so that's 3.4, quantity squared, 17%.
So then it's RS also, right? Or something.
Yeah. Well, I mean, we could do it either way. We could do RP like it did there, or we could do RS and have the minus sign, but it goes away because we're squaring it. Either way. Okay. So this is one reason why a diamond on a diamond ring or other jewelry is very sparkly. Is because there's a lot of reflection for no reflection at each interface. But sometimes you find a much less expensive option by going with zirconium. So if we had air and zirconium jewelry, so this is 1.0, this is 1.9, so the reflectance works out to be about 10%. And so zirconium jewelry is not as sparkly as diamond jewelry because it just doesn't reflect as much light at each of the interfaces. That's a heck of a lot cheaper. Then, let's do another example. Let's say we have air and rutile. Have any of you worked with rutile in the lab? Rutile is just titanium dioxide. So crystalline titanium dioxide. And so with rutile, it turns out the refractive index is even higher than diamond. It's 2.6. And so we end up with a reflectance of 19.8%. And I'll give you an example of using rutile in the lab in just a little bit. Okay. Another example. Let's say we have air and gallium arsenide. And let's do this for a wavelength of 0.85 microns. So air, refractive index 1, gallium arsenide, refractive index 3.6. So once we go out of the visible, it's possible to have materials that are transparent. They may not be transparent and visible like gallium arsenide is not, but in the near infrared they are transparent and the refractive indices get pretty high. 3.6 is very high. And so if we calculate the reflectance, what we find is that it is 32%. So almost a third of the light gets reflected. And then remember we talked about how lasers work? So laser, you always have to have optical gain, and you need feedback for cavity. And so we talked about how you can take a gallium arsenide wafer, grow some epitaxial layers on it, and then cleave it, and then you have a nice crystallographically flat surface. And then this tells us that encountering that interface, we get 1/3 of the light reflected. And then over here, again, we get about 1/3 of the light reflected. And because we have so much gain here in the epitaxial layers when we pass a current through, that even though we lose 2/3 of the light at each interface, we can still laser just fine because our gain is so high. Okay, so bottom line then is there are lots of applications for Fresnel reflection, and it's really useful to know how it works. And notice all of this is just for normal instance. So now what we need to do is take a look at non-normal instance, and there we find some really useful phenomena. Okay, so what we're going to do is sketch the relationships here for non-normal instance. And what we're going to focus on is looking at the TE case, and the reflection coefficient RS, we can always write it as having a magnitude and having a phase. And looking at this expression right here, what phases can RS have? Is RS real or complex?
It's real.
Sure looks real, right? A real number can have what phases? 0 and pi. Okay. And we're going to look at TM in the same way. Magnitude and phase. And then what we want to do is further break this down into internal and external reflection. So internal means we're in a higher index material going into a lower index material. External means we're in a lower index material going into a higher index material. And so let's see if we can get this all on the board. Let's say, let's look at TE, and we'll do internal, or no, let's do external first. And then we'll do internal. And what we want is to look at the magnitude of RS, this piece, as a function of instance angle. And we want to look at the phase as a function of instance angle. And so let's assume that N1 and N2 come from the set 1.0 and 1.5. So So if it's external, then N1 is 1, N2 is 1.5. If it's internal, N1 is 1.5, N2 is 1. So in other words, we're looking at an air-glass interface or a glass-air interface. Okay, so we've already seen for external reflection that at normal instance, and let's go over here, 90 degrees. At normal instance, what was the reflection coefficient? For the reflection coefficient?
0.2.
And was it positive or negative? It was negative. Okay, so if this is 1, 0.2 is about here, so the magnitude is going to be 0.2 at 0 degrees. And here, if we look at phase, we're up here at pi phase because we have a minus sign, right? Because in this case, RS is minus 0.2, we calculate. Okay, so now the question is what happens as we go off normal instance until we get over here to 90 degrees. And likewise over here, 90 degrees. Okay, what happens is, and this is 1, what happens is the magnitude of the reflection coefficient does that, monotonically increases to 1, and the phase just stays at pi. So you look at that, and one thing that's kind of interesting that jumps out is, hey, as you go to 90 degrees, the reflection just keeps increasing. Which means if you're really close to 90 degrees, what does that surface look like? It looks like a mirror. So large incidence angle is the same as saying low grazing angle. So a glass surface at low grazing angle just looks like a mirror. So does that have any practical application to you? Actually, it does. When you get up in the morning and you get ready for the day, usually you stand in front of a mirror and shave or comb your hair or whatever. And so if you're doing that, here's a mirror. What does the mirror consist of?
Glass and aluminum.
Glass and aluminum. So this is the glass. Where's the aluminum?
On the back side.
The back side. So you have this thin film of aluminum on the back side. If you look at it from this side, what do you see?
Opaque.
It's opaque. It doesn't look very shiny. It doesn't look shiny at all. It just looks like this kind of rough metallic surface. And so basically what's happened is some aluminum, you melt it, and you just splat it onto the back of the glass, and that back surface just doesn't turn out to be very flat, and it oxidizes immediately anyway, so you get aluminum oxide covering the metal. And so it just doesn't look very mirror-like. It's not flat, and it's not actually aluminum on the surface of it, it's aluminum oxide. But the aluminum that's next to the glass, it's protected from the atmosphere, so no oxidation. And it's on a very flat piece of glass, so it's flat. So that means that surface looks very mirror-like. Okay, so when you look in the mirror, you've got the ambient room light that's scattering off of your face and whatever else. And so when you look in the mirror, in order for you to see anything, like let's say, I don't know, you're looking at your hand. And so you've got this scattered light coming off your hand, and it's going everywhere, right? But the only light that you care about, that you see, is the scattered light that comes over here and then somehow makes it into the pupil of your eye. And then gets focused to the retina. That's the only light you see. And so that light, how does it get there? Well, there's a front surface reflection here, and there's a back surface reflection here. Which is stronger? Back surface reflection. Front surface reflection is approximately what? 4% of the ambient light. So most of the light gets reflected off the back surface and makes it into your eye. So that's what you see, is that back surface reflection. Now what if you took that mirror and you tilted it? You wouldn't be looking at you anymore. You'd be looking at some other part of the bathroom. But if you took that mirror and tilted it like this until you're at a low grazing angle, then what?
It'd be even more it's brighter.
Yeah, you'd have, let's do it this way. So here's the glass, here's the aluminum. If you're looking straight on, you get 4% here, and most of the rest of it here. And you get another 4% lost there, but you won't worry about that. So the light is pretty much being reflected off the aluminum surface that you see. But as you go off normal instance here, so the light's coming in this way, then you get most of the light actually reflecting here. Some of it goes in and reflects there, but most of it gets reflected off the front surface because you're over here. So when you go to low grazing angles, you're actually seeing the reflection off the front surface of the glass, not the back surface. So what happens in between?
Combination of both.
Combination of both. So when you're standing in front of your mirror tonight or tomorrow morning, and you're looking at your beautiful self, go off normal axis and just see some other object, and you'll get to a point where you actually see two of them. Because the amount of light being reflected from the front surface is comparable to the amount of light being seen from or reflected from the back surface. And they're going to be shifted a little bit because of this difference in path length. And so you'll see this double image. So just notice that. And then keep going to low grazing instance, and then it's just going to look like a great mirror because it's all reflecting off the front surface.
So the double image is present in the straight-on case as well. It's just really weak in comparison, so you don't see it.
So you don't notice it. Yeah. I mean, you could actually set up an experiment so that you would measure it and see it. And the way to do that is, I won't get into it, but it's there. It's just that your visual system doesn't respond to it because it's so weak in comparison to the main signal. So, yeah. Okay, and notice that all just falls out of the Fresnel reflection from the dielectric surface. Okay, so that's for external reflection. If we do internal reflection, then we're inside the glass trying to get out into the air. And we're looking at the reflection. So if we plot the magnitude, I guess I'll move this label. So we're going to plot magnitude as a function of angle. So here's 90 degrees, 0 degrees. And if we calculate RS, it's going to be 1.5 minus 1 over 1.5 plus 1 because N1 is 1.5 and N2 is 1. And so that's going to be 0.2. So here, we're at 0.2. And then looking over here at phase, we're here at 0, right? positive 0.2. Okay, so now what happens as we go off normal instance is this goes up like that and hits unity and stays at unity to over here at 90 degrees. And we hit unity at what we call the critical angle. And for all instance angles at or beyond the critical angle, we get total internal reflection. So all of the light gets reflected by this interface. No metal involved. And then if we look at phase, what happens with the phase is it stays 0 till we get to the critical angle, and then it does something like this.
That's weird.
Yes, so in this region, is the reflection coefficient real? No, it's complex. So this becomes a complex number. How can that possibly be? Turns out there's no loss. So we'll dig into that. We'll see how it works. But basically, theta 2 is the problem. Because we need, when we go back to Snell's law, we need sine of theta 2 to be bigger than 1, which it obviously cannot be. So we'll see how to deal with that. Okay, but at any rate, this is the picture for TE polarization. Now let's do the same, but for TM, and then we'll dive into the interesting things that we're finding here. So TM, we want external reflection and internal reflection. And so what we want to do is plot the magnitude of RP as a function of theta 1. And we want to plot the phase of the reflection coefficient. And so if we start out at 0 degrees, what is R sub P? Yeah, so over here, the cosines are 1, so it's n2 minus n1 over n2 plus n1. It's external reflection, so n1 is 1, n2 is 1.5. So that means RP is plus 0.2. So here we start off at plus 0.2, and over here we start off at 0. Okay, good. Now, what happens is that as we go off normal instance, the magnitude of the reflection coefficient does not increase. And over here, it increased. But over here, it does not increase. Instead, it dips down until we hit the Brewster angle, and then it goes up until it's back at 1 at 90 degrees. And the phase stays at 0 until we hit the Brewster angle, and then it flips and goes to pi. So for TM light, when we get to high incidence angles, low grazing angles, the surface still looks like a mirror. But in getting there, we actually go through an angle where we have no reflection at all, which is at the Brewster angle. So for TM polarized light, we can find an incidence angle where we have no reflected light. It all gets transmitted. So the interface is lossless for that polarization.
So this angle is the angle that is just reflection?
Where the reflection goes to zero.
Okay.
So all of it is transmitted. Yeah.
I'm confused on why once phase one starts at pi and phase the other starts at 0.
Okay, so here we have, so RS theta 1 equals 0 degrees is N1 minus N2.
Oh, we're just trying to get that negative sign.
Well, I mean, so this is 1, this is 1.5, so we get minus 0.2. So that's where the pi phase comes from, is that negative sign. Yeah. So over here, all we're saying is that in the TM case, between 0 degrees and the Brewster angle, it's a positive real number. And then between the Brewster angle and 90 degrees, it's a negative real number. Which means that, looking at this expression, between 0 degrees and the Brewster angle, this is bigger than that. So it's positive, the overall thing is positive. But beyond the Brewster angle, this term is less than that term. So it's a negative real number. Okay, so then for internal reflection, what we have is that we start off at positive or negative 0.2 for the reflection coefficient. Yeah, it'll be negative. So here we have 0.2 for the magnitude, and for the phase, we start off at pi. Okay, so what happens here is that, again, as we go off normal instance, the amount of field that's reflected decreases till we hit the Brewster angle, and then it increases till we hit the critical angle, and then it's unity. And then over here, what happens is we're at pi, and then we go to 0 at the Brewster angle, and then over to the critical angle, and then it does something until it gets back to unit, or back to pi at 90 degrees. So again, over here, between theta c and 90 degrees, the reflection coefficient is complex.
Is the critical angle always greater than the Brewster?
Yeah, we'll see that shortly. Okay. So, when you look at this, you can see that there are a number of interesting things happening. For external reflection, low grazing angle, it looks like a mirror for TE and for TM. For TM, whether we're external or internal, there's a Brewster angle where we have no reflected light at all. And then for internal reflection, we end up with total internal reflection past critical angle, meaning that all of the light is reflected. None of it is transmitted. So we get a perfect mirror with no metals involved. Okay, so what we want to do is dive in first and examine total internal reflection and see what's going on there. And then what we'll do, and it'll probably be next time before we get there, we want to look at Brewster angle phenomena.
Why is it called Brewster?
Oh, just sometimes Brewster was the first one we noticed it.
Because it seems like Fresnel but no one was discovered in that Brewster.
Yeah, well, I think Brewster actually preceded Fresnel. Yeah, so. Yeah, but, oh well. Okay, so, Okay, so you've got these graphs kind of written down and firmly embedded in your mind, right? Okay, so let's go. Yes, that's what we want. Okay, so let's look at total internal reflection. And basically, if we draw our interface between materials 1 and material 2, and we come in with a plane wave at some incidence angle theta 1, and n1 of course is bigger than n2. And basically what's happening is our refracted wave is going off at some angle theta 2 bigger than theta 1. And this is described by Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. If I solve for sine theta 2, then that is N1 over N2 sine of theta 1. And now this illustrates our problem. And our problem is that N1 is bigger than N2. And yet, theta 1 can range from 0 to 90 degrees. So this can go from 0 to 1. So the right-hand side here can go from 0 to something bigger than 1. And yet on the left-hand side, it's sine theta 2. And sine of theta 2, if theta is real, can only go between 0 and 1. So that's our problem. Okay. So instead of looking at things this way, let's solve for sine of theta 2, which is n2 over n1 sine of theta 1. And let's ask what happens when theta 1, actually, sorry, I got that backwards. Sine of theta 1 is n2 over n1 sine of theta 2. There we go. So let's look at what it takes to get theta 2 to be 90 degrees. So if this is 90 degrees, then we say that theta 1 is the critical angle, and it's n2 over n1, which is less than 1. And so the critical angle beyond which total internal reflection occurs is the arc sine of n2 over n1. So that is that critical angle there. So if we do a little example, let's say we have glass and air. Then we can calculate the critical angle as being the arc sine of 1 over 1.5, which is 42 degrees. So if theta 1 was 45 degrees, then that means I'm in total internal reflection, right? So if I had a prism like this, or just a normal right angle prism, and I had light coming in from the left, then it's going to be incident at 45 degrees, right? And all of it reflects. So a right angle prism makes a beautiful mirror in a lab setup if you need a 90-degree angle. Works great. Moreover, if I took that prism and rotated it around so that it looked like this, and I had light come in this way, well, it's incident 45 degrees there, total internally reflects. Here it's incident 45 degrees, it total internally reflects. Oh, it's a retroreflector.
Do you lose on the interfaces though? Or
Yeah,
are those
you get
coded
4%.
pretty well?
Yeah, you get 4% reflection here and here, reflection loss.
So you get 100% reflection on those this is inside of the glass.
Yeah, all of the light gets reflected here and here. So if you anti-reflection coated this surface, then this would be very efficient, optically efficient. Okay, and so if you could take, well, so this looks like a retroreflector. And if you extend it to 3 surfaces, you could actually make it a 3-dimensional retroreflector so that light coming in at any angle from within some cone would be reflected exactly back the direction it came. So when you're driving down the freeway at night and your lights are on, so the beams are going out in front of the car, and you notice that whenever you go by a freeway sign, the letters are really bright. And it's because the light from your headlights is being retroreflected from those letters back to you. So there are little tiny retroreflecting elements in the paint that gets used for that signage. And it turns out they don't use exactly this principle with corner cubes, but they do something else with spheres. But it's the same basic idea. You're getting total internal reflection to turn the light around. Okay, so let's do one other thing. Notice that for TE, I get this phase shift between the critical angle and 90 degrees. And for TM, I get something that looks kind of similar, but it turns out they're not the same. And so we could write down what they are. And for TE, the tangent of that the tangent of that phase shift over 2 is equal to the square root of sine squared theta 1 minus sine squared theta c all over cosine of theta 1. And the tangent of the phase for the TM divided by 2 is the same thing. So I'm just going to put so this whole term, and then we have 1 over sine squared theta c. So in other words, they're not the same. So I could make a really funky wave plate using this phenomenon. In fact, it's called a Fresnel ROM. If I could find an instance angle, so theta 1, such that Vs minus Vp, actually it's backwards, Vp minus Vs, is 45 degrees, and it turns out I can, then what I could do is the following. I could take a piece of glass, I could cut it so that this instance angle is exactly the one that I need, so I get a 45-degree phase shift between the TE, which is out of the plane, and the TM, which is in the plane. And then it totally internally reflects over here to this interface, instant of that same angle. And then it totally internally reflects off of that. And now here, I have 45-degree relative phase shift here, another 45-degree relative phase shift here. So my phase retardance is 90 degrees, quarter wave plate, with no birefringent material, just a simple piece of glass.
Can you explain that one more time?
Sure. So we get different phase shifts for the TE and TM, depending upon what the instance angle is, theta 1. And if I choose theta 1 such that the difference between those phase shifts is 45 degrees, then when I'm incident at this surface at that angle, the TE light will have a 45-degree phase shift with respect to the TM light. And then here I get another 45-degree phase shift of TE with respect to TM for a total of a 90-degree phase shift, which is exactly what a wave plate does. Get a 90-degree phase shift between two orthogonal linear states. So that piece of glass cut just right is a quarter wave plate. Except it's using total internal reflection, not some kind of anisotropy of the material. Okay. Yeah, Ivan?
Excuse me, so the TE is getting phase shifted away from the TM, or are they both getting phase shifted?
Well, this is the relative phase shift of TE and TM, or TE relative to TM. Because the phase shifts, you look at the functional forms, they're different. So you get a different overall, different phase shift of one compared to the other. And what we care about in polarization, what's the difference?
Oh, I see.
Okay. All right, so now this brings us to the lovely, joyful topic of evanescent waves. Because what we're saying is that I have total internal reflection, meaning N1 is bigger than N2, and the incidence angle is greater than or equal to the critical angle. Then the instant wave vector and the reflected wave vector, of course, are at the same angle, right? And then we have a transmitted wave vector at angle theta 2, but this is over here. And so we're saying all of the power coming in gets reflected. And so the question is, well, does that mean there's no field over here?
We still have to maintain the boundary condition where the fields are equal on both sides, right?
We have to maintain the boundary condition. But is there any power over here? No, there's no power transmitted into this material. But there is a field over there, because otherwise we wouldn't have the boundary conditions satisfied. So the question is, what kind of a field is over there that carries no power? And it's an evanescent field. So that's what we want to...
What field?
Evanescent. I'll write it down.
Like the band.
Yeah. Something like that. So we have an evanescent field. So we can formally write the transmitted wave vector, or transmitted electric field, as some constant complex vector Et times e to the j omega t minus k sub t dot r. Right? We can always write that. And then k sub t is just going to be k sub t x hat plus k sub t z hat, right? And because this is our z-axis, this is our x-axis. And we can write that k sub tx is just k2 sine theta 2, and kz is going to be k2 cosine theta 2. Right? Okay, and then the problem becomes, you know, this business over here, theta 2, we can't have a real angle that satisfies this. So it turns out there's an easy way to get around it, and that is to write theta 2 in terms of theta 1, because theta 1 is always well defined. So we know with Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. So let's just take sine of theta 2 and write it as n1 over n2 sine theta 1. So that means this ktx here, I can rewrite it as k2 n1 over n2 sine theta 1. And now I never have any problem, because theta 1 is always defined. And similarly, ktz is k2 cosine of theta 2, but I can write that as square root of 1 minus sine squared of theta 2. And now I can play the same game. K2, 1 minus, and then I substitute in n1 over n2 squared sine squared theta 1. And then in total internal reflection, this term is bigger than 1, right? So I can acknowledge that fact, pull the minus square root of minus 1 out, so I have plus or minus j, k2, square root, n1 over n2, quantity squared, sine squared, theta 1 minus 1. And now under the square root, that's positive, so everything's fine. Are we following? Okay. So now I have ktx, I have ktz, I have the electric field. Let's plug ktx and ktz back in for kt right here. And I'll do that over here. So we have et, and then actually I should probably have said this is et of r and t. So let's do that, et of r and t. So we have some constant complex vector et. And now this piece right here, I'm going to plug it in here and pull it out, because look, that j is going to be multiplying that j, that gives me minus 1.
Mm-hmm.
So this is going to be e to the minus plus k2 square root of this thing. So n1 over n2, quantity squared, sine squared theta 1, minus 1, and all of that is times z. Right? Because we're dot producting there with the r. And in fact, you know what I should do is I should just give this a name. Let's just call it beta. So this piece right here is beta. So this is e minus or plus beta z.
So then the omega t term is still implied, right?
Well, I haven't finished writing it down. So now we have e to the, oh, you know what? Yeah, no, we're good. Okay, so then we have e to the j omega t minus, and now I still have the ktx times x term. So that is k2 n2 over n1 over n2 sine theta 1 x. Okay? So this k then, it's got the z component, which I pulled out because I could take the j and multiply it by this j. And then it's got the x component, which stays inside of the j term here. And there's the x component. Okay, so are we good with that?
Yeah, in that exponent there, next to the plus and minus, is it, there's no j there, it's just a k?
No, because this j multiplied that j.
Oh, yeah.
Yeah. Okay, so here's where we'll end. Over here, this looks like a propagating wave, right? This looks like a plane wave. What direction is it propagating in? Which direction? Positive x direction. Where is that on our diagram? Right. It's propagating that way. It's propagating this way. Right in the direction of the interface. And then what's this right here?
Beta C.
Because we don't take the positive term because that would mean it's exponentially growing, which is unphysical. So we take the negative, e to the minus beta z. What's it doing in the z direction? It's exponentially decaying. And that's an evanescent wave. So we'll pick up there on Thursday. So we'll see you when I get back from this trip, and we'll have fun on Thursday.